This video is about my course project for digital geometric modeling, and it's called Generating 3D Shoe Models from just a single side view image. Before we look at the project, it's worth looking into why this is a project worth pursuing. And the reason is that there's a growing trend of people moving towards AR and VR, and so you need not 2D images, but you start requiring 3D models, and that's very expensive to generate and create. Not a lot of people can do that. So it's pretty useful to have solutions where you can just go from 2D to 3D, because it saves time, it saves money, it lets users customize in 2D, and then that would affect 3D. And it's just a lot easier to prototype and build things if you can edit them in 2D and then get 3D models. And these are some of the applications here. So this on the right is like the overall objective. So you just give a 2D image and you get a 3D model. But there's some certain criteria for this method. So these are criteria I came up with for the project. So the first one is that you need to be able to give a single image. So if I give that image of the shoe from the right, it should give me a 3D model. It should be fast, so I can do it in relatively real time. It should generalize, so whatever technique I use, it should work for any new input image. And the last one is that it doesn't need any 3D data. So I want to be able to have all of these criteria without needing like 3D models, like a data set of 3D models or something like that. So I just want to be able to work with images and get these 3D shoots from that. So to do this, I need a data set, or I need some sort of training data. And in this case, there's this really nice database called the Sneaker database, and they have these 360-degree shoe images. So, and there's around 7,500 shoes. So if you download for a single shoe, you would get these images, like all of these shoes from different angles. And then you can pass those through a segmentation network that's available on pytorch or torch vision, and you can get masks of these shoes, and that'll be important later on. Cool, so now I have this data set of shoes, and I have these shoes from different angles for each of them. So now what method do we go for? So the first thing that you would think of is, I think, something like COMP, which uses structure for motion and like feature matching. It's pretty powerful, but it doesn't fit all of the criteria because it needs a lot of images, and 36 isn't really enough. It's not that fast either, and it doesn't generalize. So if you do this for a single shoe, you can't use the features or things for another shoe. So you would need to do it for every single shoe. The benefit is that you don't need any 3D data. You just need images and these camera positions, and that's enough. Another approach would be to use some sort of like neural network architecture where your input is an image and your output is a 3D mesh or something. It's pretty powerful because it generalizes. That's what neural networks do, and it's fast because it's a bunch of like matrix multiplications. The downside is that you need 3D data. So if you have an input of image and output of 3D data, you need something to compare that to that 3D output to, so that you can propagate a loss, right? In this case, I have only images, so I don't have like a 3D model for each of these shoe images. So that doesn't really cut it either. The last thing is if you optimize with a differentiable renderer. So this is like relatively new and quite powerful. So I could start with like a sphere mesh, and then I could render that mesh from different angles, and I could do like an image to image loss, and I can propagate the loss back to the sphere and start deforming it. And this is pretty powerful because I don't need any 3D data. I just need to use these images and I can push the loss back. However, I need a lot of images. So in the future, if I want to try this out, I would have to get like multiple angles of a shoe to even get a 3D model, but I want to be able to do that with just one image. It's not that fast because it needs time to optimize, and it doesn't generalize. So if I optimize for a single shoe, I would need to re-optimize for other shoes. So these methods individually don't really give us a solution, but you can combine them, and combining them would help us meet all of the criteria. But because neural networks and these differentiable renderers are both differentiable, it's easy to combine them. COMP isn't really differentiable, doesn't really fit the criteria, and it's not easy to find a way to combine that with these other features. So ultimately, the solution I went for combines these two approaches, and it helps us meet all of the criteria and make all those points green. So this is the approach from like a very high level. So you start with an input image that goes to a network, and the network also gets like a base shape, and it deforms and colors that base shape based on the input image, and it outputs a mesh. So once you have the mesh, you can render that mesh from different angles, the same as the images, and you can do an image to image loss. So if you render it from the same perspective as your training images, you can get a loss, and you can propagate that back through the renderer to the network, so that the network learns to better change the mesh to fit the images. The benefit is that you don't need any of that 3D data. You can only use these images, and that's really the key here. So this is a high level. If I deep dive into it, this is what the neural network, the one on the left, looks like. So you can initialize the network with a base shape, and in this case, the base shape is actually this. It's like a rough shoe, and this is the architecture. So my input image goes in, it goes through a UNet, which outputs a flow map. And a flow map is, instead of outputting like a texture map, you can output a flow map, and a flow map is basically a lookup. So each point in the flow map corresponds to a pixel location here. And then you can multiply these two. So you can multiply these two and you can get a texture map out of that. The reason this is done is because if you try to get a texture map as an output, it's a huge color space that the model needs to traverse and understand. But you know that the colors of your texture will be the same as the colors from the image. So you can pinpoint colors from here and use that to build a texture map. So cool. So the unit outputs this flow map, which can give you a texture map. But to get the shape, what we do is that you look at the encoded features from the unit and you pass those through a shape decoder that give you these vertices. If I click on that, yeah. So the shape decoder, it takes the unit features, it passes them through another set of connected layers. And then those new features go through like 3 separate layers. The first layer gives you an offset. So it basically shifts the base shape. The second one gives you biases. So each of the vertices in base shape get deformed in a certain way. And the last one is a scaling factor. So it multiplies to all the vertices. So if you look at the neural network here, I can go back to that. Yeah, in the neural network, you can initialize it with a base shape. And it would initialize with the vertices, the faces, and the UV points. And so once you have that base shape initialized, you can offset it with the center that's output. You can change the shape with the biases that are output, and then you can scale it with that factor. So the network can basically take the base shape, move it a bit, scale it a bit, and deform it. So it's allowed to do all those 3 things. Cool. So now you have a vertices output, you have a texture map output. The faces and the UV points stay the same from the base shape that you save in the network. And now you have a mesh. But initially that mesh will be some random shape and random color because the network's not trained. So to train the network, you use a differentiable renderer. So that's where the second part is. So you render that mesh from the same perspectives as your training images. And then you would initially get some blob like this, but then you can do a loss between that blob and what it should look like, what the image looks like. And you can do an image to image loss, an L1 or L2 loss. It's L2 in this case. And the differential renderer also gives you like the mask. So to give you a mask of this. And we already got the masks from these images using the segmentation network. So now you can do an intersection over union loss. So the reason you do both of them is because the mask helps deform the shape and the image loss helps texture the shape. And both of those things are very important. I also added a perceptual loss. I won't deep dive into it, but it basically helps refine the colors and optimize it a bit faster. So everything in green here is a loss that's on the network. So I have mesh regularizers here like bunched up, but essentially there's 2 in here. So the first one is the Laplacian regularizer, which helps smoothen the mesh because I don't want the mesh to grow and twist and turn. So the Laplacian helps smooths it. And there's also a flatten loss, which is actually, it tries to keep the normals between faces similar. So it doesn't let the mesh bend or twist. It keeps the normals in the same direction, or it tries to keep them in the same. You need these things because if you don't have them, your mesh because you try to optimize your mesh based on the image loss, it would just grow and twist and turn, but the mesh regularizer keeps it smooth and even. So it's like, it's a lot smoother and nicer. Also, to speed up the optimization, there's a flow loss. So when you output a flow map, you're basically pointing to a pixel in the original image. And a lot of the original image is actually just a white background and you don't need that information. So you can guide the flow map to focus on the shoe. So to do that, you multiply the flow map with the mask of this image. And because the mask could be a value of 1 where the shoe is and a value of 0 of where the background is. So if all of your points in the flow map correspond to the shoe, like inside the shoe area, if you multiply this with the mask, it would be a large value. It would be like an optimal value because all of the points point to somewhere inside the shoe. So that's what the flow loss does. It tries to make sure that every point in the flow map is actually inside the shoe and not focusing on the background. And it does that by multiplying by the mask. So all of these different losses help not only optimize it, but speed up optimization. And these are like picked from different papers and things like that. And you could easily get decent results like just by training like for I think 12 hours or like 200 to 300 epochs. Yeah, so this is a slide of a result from around 200 epochs or 250 epochs, where you have these 2 input images on the left, and then you get these 2 meshes for them on the right. And it's pretty cool because it picks out like the Nike logo and even the words Air, it starts to pick them out pretty early on. Okay, I have a web demo set up, so you could actually test it out. So if you go to the web demo page, it has this base image and this is the base output. But I have some images here of different shoes that I can drag in. So if I drag this one in, so this is like a blue Nike shoe, and hopefully that runs, yeah. And then this is the output mesh for that input image. And it's pretty cool because once you've trained your model, you can, if I go back to that slide. So once your model is trained, you can remove the differentiable renderer and your network is pretty good. So you're starting to get decent meshes out of it. And then this is an example of that. So you can run this pretty fast. And here's another example of a yellow shoe, Nike Pollen. And you can see that the shape is different too because it's stretched out for the high top. Let me find another one. Oh, this is the same shoe in a different color. Yeah, it's completely different texture map here. Let's see what else I have. Here's another example of a New Balance shoe. You can see the N over here, and it's picked that up along with the little mesh colors. And if you go to the other side, it's pretty interesting. It's the N, but reversed. So something I realized when you train this network, it learns on its own that the other side of the shoe is basically the flipped version of this side of the shoe. And it works in many cases, except in a situation like this, where the New Balance logo on the other side should actually be reversed. Yeah, I just found that pretty interesting, that it learned this on its own. I didn't have to give it that information. I'll go back to the slides here. It works pretty well. And if I leave it training a lot longer, I think it would overfit, and that would ultimately help as well. But there are some issues. And the first issue is when you feed that base shape into the network, it uses the UV points. So the UV map that you have for the base shape is the one that's used. The UV location that you have in the base shape are the ones that's used in your output. So this is my base shape in the web demo and all these examples. And you see that I have islands. So I'm not a pretty good 3D artist. So I set it up as islands so it's interpretable to me, so that when I look at the texture, I can see that, okay, it's learning properly. But one consequence is that if you do this sort of island-based unwrapping, it doesn't match up very well. So if you look at this side of the shoe and you look at this side of the shoe, they're actually the same. So they should have the same colors, but in your output, you would see that it's pretty different, because it's hard for the network to understand that I need to have exact same pixel colors on this line along with the same pixel colors on this line. So a quick solution to this is to do a spherical unwrapping, where you unwrap it, maybe if you cut through the bottom of the shoe, and then you can have the colors flow properly across, and you wouldn't have this texture flow issue. You can also adjust the flow map to pick points that are similar. So you don't want the flow map to pick a point here and then pick a point here. You can ask it to pick in a similar region, and that would just keep the colors flowing consistently, and that would greatly improve the texture map. Another issue is that of invariance, and this is also another one that can be fixed pretty easily. So if you look on the left, the two images are the same to us, but to the network, they're pretty different, and the outputs are drastically different. And the difference is just this little white gap here. And that's because there's no sort of, when I trained my network, I didn't have any data augmentation, but I should actually go back and train with some augmentation to prevent this problem from coming up. And the final issue is of imperfect geometry. So if you look at the right, that's the base shape, and it's a pretty clean looking mesh, but on the left is an output of the network, and that mesh is quite tangled, and the triangles aren't smooth. And there's a lot of different solutions to this in papers that have come out recently. But you could do things like you could remesh at certain intervals, or you could create a new base shape every 100 epochs and then remesh that shape to keep it clean. But there's also other solutions about how you deform meshes and you make sure that these triangles don't go out of control. Yeah, but in conclusion, it's a pretty fun project that surprisingly worked a lot better than I expected. And the issues in here are quite easily fixable. Like the ones that I highlighted here, it shouldn't be difficult to fix. And it would be pretty nice to have it as a product that everyone could use.